Okay, this is really just an introduction into logs. We start off by looking at the graph of a log function, and that would be the red graph right here. And what I also did was I'm showing you the graph of the exponential function. So this red graph is the graph of log of x, and this blue graph is the graph of 10 to the x. Now, they are inverses of each other, and we can tell that because they both reflect over this line right here, which happens to be y equals x. So that kind of leads us into the discussion of what is a log. So let's take a look at that. If we start off with an expression, let's say log 5 of 25 equals 2. That can be rewritten as 5 to the second equals 25. And so if we just really focus here for a second on the 2 part of it, right? If I'm saying the log is equal to 2, then what I'm really saying is the log must be equal to the exponent. And that's really what a log is. A log is an exponent. So that being said, what we want to make sure we know how to do is rewrite logs as exponential functions. We want to be able to evaluate them also. So let's look at a couple examples. Let's suppose we were asked to rewrite this expression, log with the base of a with the result of b being equal to x, as an exponential function, right? Well, one of the little tricks that we use a lot of times is we do something called the loop-de-loop. So we start at the base always, loop around this way, finish that way. What would that look like? A to the x power equals b. Now you can do this the other way as well. So let's say we start with 10 to the third power equals 100. We could do the loop-de-loop again. Start with the base, loop around, and end there. So what would the equivalent log expression be? Log with a base of 10 of 100 equals 3. Again, whatever you have after the equal sign needs to be the exponent because, again, a log is an exponent. So just a quick review right there of rewriting exponential functions as log functions and log functions as exponential functions. Let's evaluate a couple logs. Let's say we were asked to do the log with a base of 7 of 149. Right, what does that equal? Well, we know that 7 to some power equals 1 over 49. If this gives you a little trouble, what you might want to do is look at the connection between 7 and 49. Most people know that 7 squared is 49. So how can I rewrite 7 to a power to get it equal to 49? Well, that would be 7 squared. How can I bring that up out of the denominator? Well, that would be using the property of negative exponents, right? So 7 to the negative second is the same thing as 1 over 7 to the positive second. So in that case, now that we see that, we can kind of confidently make the connection that x must equal negative 2. Let's try another one. What's the log with a base of, let's say 9 of 3. Okay, again, 9 to some power equals 3. The problem I have again is these are not the same bases, right? So it might help to make 9 written as a base of 3 squared, right? Now, don't forget that you still have that x, right? That never went anywhere. So 3 squared to the x is equal to 3, and obviously that would really technically be 3 to the first. Now look at that, right? What do we do when we multiply? When we raise a power to a power, we multiply exponents. That's really 2x. We could set that equal to 1, right? So x must equal 1/2. Now the reason that makes a lot of sense, let's go over here for a second, is because anytime you have 1/2 as a power, x to the 1/2, y to the 1/2, 9 to the 1/2, which is what we have here, that 1/2 indicates the square root. So this would be the square root of x, the square root of y, the square root of 9. And if you think about it, why does this make sense? Well, the square root of 9 definitely equals 3. How would it look if we had an equation? Log of 5, 2x minus 8 equals 2. Well, here's a good chance to use our loop-de-loop. 5 to the second power must equal 2x minus 8. So what you've done is you've taken a log expression, created an exponential function right here, right? And now we've really created an equation that we can solve. 5 squared is 25, and we're just looking for x here, right? So we'll add 8 to the other side. That'll be 33. Divide by 2, and so x equals 33 over 2. Okay, let's look at part 2. Part 2 really is just looking at general properties of logs. And there's 3 basic properties we want to remember. One of them is when you have a log of a product, let's say m times n, that can be rewritten as log m plus log n. Second property, when you have the log of a quotient, log of m over n, that can be rewritten as log of the numerator minus log of the denominator. Third property, if I have log of a number and that number is raised to a power, that is the same thing as bringing the power in front and multiplying it times the log of the number. So let's look at a couple examples. Let's expand the following expression. Log x to the third y over z to the fifth. Well, what I notice here is a couple things. First off, there's 3 different variables, right? There's x right here, there's y, and there's z to the fifth, right? The x and the y are being combined by multiplication, so that tells me that I'm going to have to separate them using addition of logs. And then the numerator is obviously being separated from the denominator by division. That tells me I'm going to need subtraction. So how can I expand this? Well, I can start by saying it would need to be log of x to the third plus log of y minus log of z to the fifth. But remember before we said that there are some properties involving those exponents. That can come down and that can come down. So my final answer should be 3 log x plus log y minus 5 log z. Let's go the other way. Let's write our expression as a single log. So let's say we have log x minus 3 minus log x plus 8 plus 6 log y. Okay, first thing I want to pick up on is the fact that I have a minus sign and a plus sign. So this minus sign is going to mean division of logs, right? This plus sign is going to mean multiplication of logs. So now, even though we don't have them in the same order, what I could do if I wanted to is I could write log of x minus 3 plus 6 log y, so that I can combine those two as multiplication, minus log of x plus 8. Now, I didn't really change the problem, I just rearranged the order. And then I could put this in the denominator. So my final single log would be x minus 3 on top times y to the 6th over x plus 8. So that should take you through the introduction to logs and log properties.